So last week we learned about arithmetic sequences. Today's lesson is on geometric sequences. So let's start with a very famous story that shows the power of geometric sequences. It's about the invention of chess. The story had happened in Persia, or maybe India, where the Shah, who was the king, was so delighted by the game of chess that he invited its creator to his court to ask him to make any wish as a reward for creating the game. The clever inventor said, "O generous Shah, all I ask is that you place 1 grain of rice," it's probably wheat, "on the first square, 2 grains on the second square, 4 grains on the third square, and continue doubling until you reach the 64th square." "Is that all you ask for?" laughed the Shah. "I would have happily given you a fortune in gold, but if that is your request, I promise you shall have it." With this promise made, an imperceptible grin spread over the inventor's face as he bowed and took his leave of the Shah. The court mathematician was in attendance and overheard this conversation. "O powerful Shah," began the alarmed mathematician, "we cannot meet his request. It would bankrupt the kingdom." After the Shah heard the explanation, he summoned his guards to bring him the inventor, and either had him beheaded for his insolence or hired him as a court minister. It probably would have been smart to do the latter. So the question is, how many grains of rice or wheat would have been required to satisfy the request? The request was asking the king to sum the terms of a geometric series, 1 plus 2 plus 4 plus 8. You see, we're doubling each successive term. The total amount of grains is about 2 to the 64th, or it's actually 2 to the 64th minus 1, which is enough to feed 100 tons of rice to every single human on the planet. So with a geometric series, things can blow up really quickly. In high school biology, you'll learn about binary fission. It's the process by which bacteria divide into identical daughter cells. After 3 minutes, a bacteria divides into 2 new bacteria. New bacteria also split into 2 bacteria after 3 minutes, and so on. One bacterium gets into a cup with a nutrient solution. How many bacteria will be in the cup after 1 hour? Well, after 3 minutes, there'd be 2. After 6 minutes, there'd be 4, and so on. Every 3 minutes, the number of bacteria doubles. Since an hour contains 20 3-minute intervals, the total number of bacteria will double 20 times. So the total amount of bacteria after 1 hour would be 2 to the 20th power, which is roughly 1 million bacteria. So a sequence like 1, 2, 4, 8, etc. is called a geometric sequence. So the definition of a geometric sequence is a sequence of numbers in which the ratio between consecutive terms is the same. The ratio between consecutive terms is called the common ratio of the sequence. The common ratio is usually denoted, not very imaginatively, by the number r, the variable r. Some examples: in the geometric sequence 1, 2, 4, 8, 16, 32, the initial value a1 is 1 and r, the ratio, is 2. 3, 1, 1/3, 1/9, 1/7. We start with 3, r is a third. 1, -1, 1, -1, 1, -1, etc. We start with 1, r is -1. And 2, 2, 2, 2, 2. We start with 2, and r is 1. Not a very exciting geometric sequence, but by definition, it is still a geometric sequence. Sequences could have infinitely many terms. The general term, the nth term of a geometric sequence, may be found by using the formula: the nth term a sub n is equal to the first term a sub 1 times the common ratio to the n minus 1 power. It's interesting to go back to last week and you compare this formula with the general term of an arithmetic sequence. The sum of the terms of a geometric sequence is called the geometric series. So find the sum 1 plus 3 plus 9 plus 27 plus 81 plus 243 plus 729. Well, you could directly sum these very easily and get 1093. But what do you do if the series is a lot longer? So here's a trick. Let's multiply this sum, denoted by capital S, by the common ratio, in this case 3. So 3s is equal to 3 plus 9 plus 27, etc. It looks exactly the same as the original sum, except 1 has been replaced by 2187. So let's cleverly realize that this is equal, 3s is equal to s minus 1 plus 2187. Now we can solve for s. So we do a little algebra, and we again see that s is equal to 1093. Let's get a general formula for a geometric series. The initial term is a1, the ratio is r, and we have a total of n terms. Hence, we have the following series. The sum is equal to a plus a times r plus a times r squared until we get to the final term, a times r to the negative 1. Multiply both sides by r, subtract the initial sum, and we find the general form for the sum of a geometric sequence is the sum is equal to a times r to the n minus a divided by r minus 1. So if r equals 2, we double with each term. The formula becomes s equals a times 2 to the n minus a sub 1. Okay. Which gives us the total amount of grains the Shah owes the inventor of chess. What about an infinite geometric series? The series goes on forever in an infinite geometric series, as Buzz Lightyear would say, with a constant ratio between successive terms. What is the sum of the elements of an infinite geometric series? Well, if the ratio is greater than or equal to 1, the sum is infinite, since we have an infinite number of non-zero terms that are either staying constant, if r equals 1, or growing, if r is greater than 1. If r is less than 1, however, the series is said to converge. It is possible to calculate the value of the sum of the elements in the series. Find the sum of 1/2 plus 1/4 plus 1/8 going on to infinity. Okay, we use the same trick we did before. Let s equal the sum of the elements in the series. Now multiply both sides by the common ratio. In this case, the common ratio was 1/2, so we're actually going to multiply both sides by 2. So 2s equals 1 plus 1/2 plus 1/4. But wait, isn't the right-hand side of the equation just 1 plus s? It is. So 2s equals 1 plus s, subtracting s from both sides, s equals 1. In other words, the sum of 1/2 plus 1/4 plus etc. to infinity is equal to 1. For positive numbers r less than 1, as n becomes arbitrarily large, r to the n power tends to 0. And taking what we call the limit of the sequence, we can consider r to the n to be equal to 0 when n goes to infinity. Let's apply this to the formula for the sum of a geometric sequence. When r is between -1 and 1, and for an infinite sequence, s equals a times r to the n minus a divided by r minus 1. But r to the n, because r is between -1 and 1, as n goes to infinity, this term goes to 0. So this simplifies as -a over r minus 1, or a divided by 1 minus r. So the sum of an infinite geometric series with a common ratio less than 1, s equals a over 1 minus r. Okay, the famous story of Achilles and the tortoise and Zeno's paradox. So Zeno of Elea was a Greek philosopher born around 490 BC. He wrote a book featuring 40 paradoxes, so of which Achilles and the tortoise is perhaps the most famous. Achilles, the ancient Greek hero, is chasing after a tortoise. Achilles is much faster than the tortoise, so he must eventually catch up with it. Zeno argued that on his way to catching the tortoise, Achilles must first reach the tortoise's starting point. But by the time he has reached this, the tortoise will have moved further forward to a new point. By the time Achilles reaches this new point, the tortoise will have moved a bit further forward and so on. So every time Achilles reaches the point where the tortoise was, the tortoise has moved forwards to a new point. Hence, Achilles will never catch up. Well, that's why this is a paradox. That logic on the surface seems irrefutably true, and yet we also know intuitively that Achilles will catch the tortoise. So let's see where Zeno went astray. Let's say Achilles runs 10 meters per second, and the tortoise's speed is 0.1 meters per second, and the initial distance between them was 100 meters. After 10 seconds, Achilles has run 100 meters, and the tortoise has crawled only 1 meter. In the next 0.1 seconds, Achilles runs 1 meter, and the tortoise crawls 0.01 meters, and so on. The distance and time will form an infinite geometric series. The distance traveled is 100 plus 1 plus 0.01 plus 10 to the minus 4th, and so on. And the time goes 10 plus 0.1 plus 0.001 plus 10 to the minus 5, and so on. So let's find the sums. The distance, using our formula for an infinite geometric series, we have 100 over 1 minus 0.01, which equals 100 over 0.99, which is 101.0101, etc. meters. Okay. The time is equal to 10 divided by 1 minus 0.01, which is 10 divided by 0.99, which is approximately 10.101 seconds. As we see, never will happen 10.1 seconds after the race begins, and Achilles catches the tortoise almost immediately after he gets to the tortoise's starting point. So that last example of Achilles and the tortoise may have made you realize that you can generate a lot of repeating decimal patterns and then solve for them using geometric series. So, in some cases, we instantly recognize the fractional representations for some repeating decimals. For example, 0.3333 onto infinity is equal to a third, 0.111 onto infinity is equal to 1 over 9. A repeating decimal can be represented as an infinite geometric series, and the sum of that series can be used to calculate the fractional representation for that repeating decimal. For example, suppose we're asked to represent 0.4444 to infinity as a common fraction. Well, this is simply the sum of an infinite geometric series, 0.4 plus 0.4 times the ratio 0.1 plus 0.4 times the ratio 0.1 squared, and so on. So S is equal to 0.4 plus 0.4 times 0.1, and so on, multiplying both sides by 10. 10S is equal to 4 plus the original series. So 10S is equal to 4 plus S. Subtracting S from both sides, 9S is equal to 4. S is equal to 4/9. Well, what if there is more than one repeating digit in the decimal, such as the repeating decimal 0.81, 0.81 onto infinity? We once again represent the sum of the geometric series, but now R is 0.01. So S is equal to 0.81 plus 0.81 times 0.01 plus 0.81 times 0.01 squared onto infinity. We multiply both sides by 100, and we get 100S is equal to 81 plus S. 99s is equal to 81, s is equal to 81 over 99. So in general, every repeating decimal fraction with a period of length n may be represented as a common fraction. So we start 0.A1, A2 through AN, and then we repeat again. So there are n digits until we start to repeat. We then make that 0 point, again, just up to the n, divided by 1 minus 0.0001. So you basically get the fraction is equal to the repeating decimals, so one period of the repeating decimals. And if there are n decimal places, we divide that by 9, a series of 9s that are n digits long. Okay, on to the exercises for this week. Find the third term in the geometric series, 2, 3. Number 2, the first term of a geometric sequence is 1. The third term is 4. Find the second term. And is your answer the only possible one? And if not, give a second answer. 3, express the repeating decimal 0.63, 0.63, 63, etc. as a fraction. Express the repeating decimal 0.942857, 142, 857, 14, etc. as a fraction. For what value of x does the infinite geometric series 1 plus x squared plus x cubed and so on equal 4? 6. If we subtract the geometric series 1 plus a quarter plus a 16th plus etc. from the infinite geometric series 1 plus a half plus a quarter, etc., what is the sum of the resulting infinite geometric series? 7. Find a digit d so that 0.d25 is equal to n over 810 for some positive integer n. And finally, find a geometric sequence in which 8, 18, and 27 are terms, though not necessarily adjacent. Okay, consider the alternating geometric series 1 minus a half plus a quarter minus an eighth and so on. What is the sum of all of the positive terms in the series? What is the sum of all the negative terms in the series? And then show that when you add these two sums together, the sum of the entire series agrees with the formula for an infinite geometric series whose first term is 1, with a value of r equals -1/2. 2. Let capital N be defined as the infinite series of square roots shown below. What is the value of n? So n equals the square root of 2021 times the square root of 2021 times the square root. Okay, so some clever manipulation to both sides of the equation hopefully will lead you to the answer. 3. Find the way to represent a fraction started 0.010204081632 with just 4 symbols. 4. A sequel to the Pirates Capturing Math Olympiad students. A pirate captures 4 Math Olympiad team members named Alex, Beth, Colette, and Daniel, but we'll call them A, B, C, and D for short. He hands them a standard pair of 6-sided dice and says, "I'm going to have some fun with you. You will take turns rolling the dice in alphabetical order, beginning with A, and then every time D goes, we go back to A, and keep rolling until one of you rolls the dice so they sum to 7. I will set the first kid to roll a 7 free and execute the rest, unless you can tell me what the probability of Daniel winning the game is, in which case I will let you all go." What is the answer to the pirate's question? In other words, what is the probability that the last of the 4 players to roll will win this game? Consider next Would Daniel's odds of winning go up or down if players needed to roll the much less likely double 6 instead of 7 to win the game? So that's all for this week. Hope you enjoyed the lesson and working on the problems, and see you all again next week.